Hey, this is another project, another Vivado tutorial project. In this one, I want to walk you through the process of connecting the processor logic and the FPGA fabric together. So I'm going to go ahead and start this whole process as if it was a brand new project. And so we're going to make a new project. I'm going to call it Project 2. It's another RTL project. We're going to skip through all of this stuff. I'm once again going to choose the Z board and let this empty project be created. To create the structure for the processing side, we actually, instead of creating an IP and creating Verilog files, we actually want to work through this IP integrator and create a block design. And this block design is going to have high-level connections between existing IP from the IP catalog. And I'm going to get this started now. I'm in the blank design. I'm going to get this started by adding the Z-board Zinc system down here at the very bottom, the Zinc 7 processing system, and let that add. And let's see, we can make this full screen. Xilinx is quite helpful here. This designer assistance window is going to pop up periodically, and it's going to allow us to do this run block automation. And I'm just going to walk it through, and whenever it pops up, let the automation do its job. So at this point, we've connected the Zinc to the external DDR memory that's on the Z board. And I could theoretically walk through this customization wizard and turn on or turn off different aspects of the system, the processing system. So for example, I could turn on UART 0, which might be kind of handy in order to, for instance, be able to see the output from the C language program we're going to build later on. But other than that, we're kind of done with this block diagram for the time being. The other thing that I need to be able to do now is to create a custom piece of intellectual property that's going to be our FPGA design. And to do that, I'm going to use Tools and then Create and Package New IP. And I'm going to walk through this wizard. I want to create a new AXI4 peripheral. Remember, the AXI bus is what connects the ARM to the external peripherals. And so we could call it whatever we want to call it here. I'm going to call it Blinker IP. And it's going to create this in a shared repository. In this case, this repository is unique to this project. If you know that you're going to be using a bunch of different projects that share the same IP, you could actually have repositories in some shared location, and then multiple projects could use it. But we're just going to start with this one. For this particular project, I don't need to have anything fancy. I'm going to allow my Verilog design to interface to the AXI bus, and that's it. We're going to be a slave to the AXI bus. We're not going to be a master where we can initiate transactions with other devices. I don't need interrupt support. The default number of registers is more than sufficient for what I need here, and so I'm going to say add to the IP repository. And at this point now, I can go back to the IP catalog, and if I browse through here, there's my Blinker IP. And if I double click on it, I can then add IP to the block diagram. And so now my custom IP is part of our project here. I'm actually not going to run this connection automation this instant. I want to make some changes to this Blinker IP. I want to connect it to the LEDs that are on the Z board and the switches that are on the Z board. So I'm going to right click on the project or right click on the block here, and I want to edit an IP packager. This is an option that's going to allow me to make changes to this device. It's actually going to open up another Vivado instance on top of this one. Okay, so now I'm in this overlay, this other Vivado project, and if I expand this, I see that I have a Vivado IP and I have an AXI IP. The way that these files are organized is the top level IP is a pass-through. All of the signals for the AXI bus pass straight through this top level module into another layer down, into the user module. So if we take a look at that in the hierarchy, this is the next layer down, and this module is actually handling the AXI bus transactions. All of the signals that arrive to this module are from the AXI bus at this point, and what it's trying to do is mediate any kind of memory read or memory write. The 4 registers that we requested in the wizard are present here as slave reg 0, 1, 2, or 3. And there's a whole series, I'm just kind of scrolling down through this file, where it's monitoring the signals coming in from AXI bus and trying to either read or write to those registers. So this is the logic here. This is implement a memory mapped register write. And so if the memory bus is indicating a write to one of our 4 register memory addresses, then we're going to capture that data from the AXI bus and store it into the appropriate slave register. So 0 bytes away from the beginning of our memory address is slave reg 0, 4 bytes later is reg 1, 4 bytes after that is reg 2, and 4 bytes after that is reg 3. And we see here all we're doing in this logic is a simple case statement looking for a matching address and copying it into 0, 1, 2, or 3. Further down we have the logic to handle reads from the AXI bus, and this is detecting a change on any of the registers that are in here, and whenever there's been a change it will assign the value from the slave register that's been stored or indicated in the read address part of the bus request, and assign its data to the output of the AXI bus. So when this module has been selected for reading, then we'll drive the data into whoever has been trying to read from us. And again, we're going to be using the address 0 bytes away from the beginning. The start address is reg 0, 4 bytes later is 1, 2, and 3, and so on. Now, that's fine. That's all well and good. We've memory mapped 12 bytes of memory. I'm sorry, 16 bytes of memory. We have four 32-bit registers, 4 bytes each. But our goal here is to connect these to the blinky lights, the LEDs that are on the Z board. And so what I really want to be able to do is take the LEDs, the 8 bits that correspond to the LEDs, and maybe have them be mapped into one of the register values, so that if you put a value on the LED, on the register, the LEDs will match. And then I want to be able to read from the switches, the toggle switches that are present on the board. There's 8 of those, and so I want to be able to map the switches and be able to read the values of the switches, but you can't write to the value of the switches, just like it doesn't make any sense to read from the LEDs. So to do this, what I want to do is I'm going to use these 4 registers, and one of the first things I'm going to do is I always like to have some kind of a sanity check. I'm going to take one of the registers and use it as a who am I, and I'm going to have it return just some value in hexadecimal. And if you read from this register, you should always get 323D feed, and that way I can use this to make sure that my program is talking to the right device. Now, if I'm reading from, say, slave reg 1, what I want to be able to do is have that maybe be the switches. And so I need to be able to see the value coming in on the switches. So to do that, what I'm going to do is I'm going to go back to the top of the file, and where it says user ports added here, I'm going to have an input wire that is 7 bits long, and that's going to be switches in. And I'm going to have an output wire that's 8 bits wide, and that's going to be LEDs out. Alright, so now if I go down to the bottom of the file again, this is where we were reading from slave reg 1. instead of reading from slave reg 1, I want to read 24 bits of zeros followed by switches in. And so whatever 8-bit values are connected to those incoming signals, when I read from this register, instead of getting the value that was previously stored there, I'm going to get those 8 bits. By the same token, register 0 is going to hold the bottom 8 bits that are going to be used to drive the LEDs. And so if you write to slave reg 0, that's going to change the LEDs. And to make that happen, I want to just add somewhere an assignment statement and say LEDs out is equal to slave reg 0 bits 7 through 0. So the lowest 8 bits of slave reg 0 will be used to drive the LEDs. Okay, so at this point we've made some changes to this module. If we just kind of double check ourselves, we've connected LEDs out to the bottom 8 bits of reg 0. We've connected the switches in to the bottom 8 bits of register 1. We are just using register 2 as a empty throwaway register. You can read and write to it as much as you like. Register 4, you can write to it, but if you read to it, you're only ever going to get the magic value. And that's actually what we call these. We call these magic numbers. So I always want to look for that magic just to make sure that I have the right values. So now I've made these signals appear in this bottom device, but remember it's a child of this top level device. And so I need to modify the device here, this blinker IP AXI, this thing. And now I need to add the additional signals that we've put in. We can put them anywhere by using this dot notation, and we had switches in will correspond to switches in, and we had LEDs out, which will correspond to LEDs out. Now I need to actually have those wires, and so I'm going to modify this parameter to have input wire 7:0 switches in and output wire 7:0 LEDs out. And that took care of the input and the output. So now that we've made those changes, I can close the Verilog files. The one last thing I've got to do is the IP, the actual IP package information itself, has some information that I need to update. So for example, the version number right now is 1.0, that's fine. We can even, if you really want, you can put your name here and you can put information about it. We can go in, and anytime that there's an update, it's going to change from that green check mark to this edit box, and I'm going to say merge from the changes, and here's our custom parameters. I'm going to merge those changes. It's giving me a warning about a clock. There's nothing we can do about that at this point, so I'm just going to ignore that. I want to make sure here switches in is listed as in and LEDs out is listed as out, so now it's found the new ports that we've created. We haven't changed anything here, I haven't changed anything there, and at this point we can generate the package. And so let's see, create and package new IP. Actually, I don't think we need to do that. Let's see here. We just want to update. But one thing we want to do before we leave here is just make sure we go through synthesis. If there's a syntax error in our code, we don't want to find it later on, that the tools don't do a good job of reporting when there's been an error. So I'm going to go ahead and let this synthesize, and we will come back when that's done. Okay, so it only took about 30 seconds. Synthesis completed successfully, no syntax errors in the file. At this point, I'm going to go ahead and close out of the Blinker IP project. Remember, this was a Vivado window that was opened for me to edit this IP, and I'm going to go ahead and close it. And now I'm back to the first Vivado window, our project 2 with our processing system in it. And at this point, I'm going to get rid of the IP that I've just added. And I'm going to go back to the IP catalog, and I'm going to look at the blinker IP here. And if I notice that it says everything has been updated, I'm going to go ahead and add this back to my design again. And this time when I add it, we actually see the new ports. And so we know that we have the right version. And so now I'm going to run this connection automation and take the defaults. And sure enough, let's see, we can make this whole diagram be one big window. We have created an AXI bus, and we've created the connections between the processor and the AXI bus. And here we have the blinker created, and it's connected to this AXI bus. But the LEDs, those external ports, they're not connected. And so now what I need to do is add external ports. So if I right click, I can do create port, and we're going to call it LEDs, and this is going to be output, and it's going to be a vector, and it's going to be 7 to 0 for those 8 bits. And now I'm going to right click, and I'm going to we're going to try to create another port. And this one's going to be switches, and this is going to be input, and it's going to be another vector, and that's going to be 7, 0. And now what I can do is I can just drag and drop. So the switches can get connected to there, and the LEDs get connected to there. And I'll save this file. And now I'm ready to actually generate and synthesize this design. So let's make this smaller. And to do that, what I need to do is navigate through this design file and go to sources, and this click on the block design, so design 1 BD, right click on it and say create HDL wrapper. And what this is going to do is it's going to generate the HDL wrapper. It's going to look like a Verilog module, but it's really going to be implemented by this complicated block design that Vivado is going to maintain for us. I always get a little suspicious when Xilinx claims that they're going to maintain things for us, but we'll see how it does. So at this point now we're ready to go ahead and run the synthesis, and we'll let it build and see if there's any errors. So I'll hit pause here and I'll come back when this is done. Okay, we've gotten through the synthesis, and now we're ready to, looks like it's still running. One thing you will notice is this will take some more time than it has before. It's got a lot more to do to route all of this stuff together. So we'll give it a few more minutes. Okay, it took about 5 minutes this time, but it finally finished. I'm going to go ahead and do the run implementation, and just as we've done before, once this is done, the implementation, I'm not going to go on to generate. I'm going to let this finish so I can open up the design and assign the LEDs and switches to their ports on the board. Alright, so implementation finished. Again, that took just about 4 or 5 minutes. We'll go ahead and open. Okay, so I am in the implemented design, and I'm ready to do our I/O planning and place the different parts. And if I use that master constraint that we've used in the previous video, switch 7 is on M15, switch 6 is on H17, switch 5 is on H18, switch 4 is on H19, switch 3 is on F21, switch 2 is on H22, switch 1 is on G22, switch 0 is on F22, and according to the data sheet, those are all LVCMOS 1.8s. I can repeat the process for the LEDs. They're a little bit different spot in the file. So LED 7 is at U14, LED 6 is at U19, LED 5 is on W22, LED 4 is on V22, LED 3 is on U21, LED 2 is on U22, LED 1 is on T21, and LED 0 is on T22, And again, according to the data sheet, all of the LEDs are on the 3.3 volts. So we'll go ahead and save the constraint file, and we can close out of the design. And I've got to go back to verify here that they're all set. Looks like they're all set. And so now I've got to go and rerun the implementation, which is also going to rerun the synthesis. Okay, so I've actually skipped a step here. All I've done is I've gone through the implementation, I've generated the bit stream, and we're now ready to program the board. And so at this point we're going to connect to the board, download the program, and unlike before, remember before when we programmed the board with the blinking light project, the light started to blink. We may or may not see that in this case. So I see the blue light comes on that indicates the board has been programmed, but I don't see any indication that anything else has happened. I don't expect it to. Our module was set to not do anything. We have to now go to the next step. The whole reason we're doing this is I need to write some C code, and that C code needs to interface with the part. So what I need to do now is go to File, and I'm going to export the hardware. And I want to include the bit stream, and it's going to create a folder called Project 2 SDK in my Xilinx project. And now that it's exported that definition, I can now launch the SDK. This is essentially Eclipse, but it's been repackaged for Xilinx. This is the interface between C language and, well, this is how we're going to program in C language and get our C program loaded into the board. Alright, so we come up here and we actually see that we have the hardware assigned. Look, there's our blinker IP0, and this is the hardware platform. I want to make a new Xilinx project. Don't be fooled into running just a regular C project. You need to run a Xilinx application project. It's going to come up in this wizard. We're going to call it Blinker, and we're going to create a new board support package. Everything here is good to go. And yep, we'll even have Hello World as our default. And when this is all done, I should have a hello world.c file, and in here is where we do our hello C file. What I want to do is I'm going to basically get a pointer in memory to where my hardware is. And if we remember back to the settings, it had a hardware address of 43C00000. That's the first byte of memory that will correspond to my device. And so I want to get a pointer to that. So I'm going to do a volatile unsigned int pointer, and we're going to call that blinker. And I'm going to assign it directly to a pointer. This is one of those very, very few times in C language where we can just 43C00000, where I can know that some random memory address is actually the right value for a pointer. Like, you normally would never do this. But because we're right on top of the hardware, I can go directly at the memory address of my blinker, and we can actually program it. I could even verify and do if blinker of 3 does not equal 0x, let's see, whatever that value was, 3233 feed, printf warning did not find the device. I'm not 100% sure if that was the magic number or not, so I'm just going to pretend that it is. And I'm going to do what we would normally do in a microcontroller here, and we're going to read from the switches. Now, if you remember, the switches were at slave reg 0, and I want to have, slave reg 1, and I'm going to make the LEDs follow the switches. So in this case, blinker of 0 is equal to blinker of 1. And so if I were to go ahead and compile and run this program, I'm going to be able to launch right onto the hardware, and it's going to connect to the hardware, and it's going to send my C code over to the board. And if you look over at your board, you should actually see, if you toggle the switches, look at that, I can make the switches follow the board. I know it's really great camera work here, but I can kind of play with the switches and get the lights to follow. And that's actually happening in the C code. This is not the Verilog directly, but it's only because the C language is reading from one memory address and writing to another memory address, and my Verilog code has managed to connect those memory addresses to the actual hardware that we've managed to memory map our hardware into application space. Now, this has been a really fast tutorial. We're going to do some more later on, but this gets you a good idea as to how to connect the Verilog all the way through the ARM processor and into your C language program and be able to interact with them together. Thanks a lot. Hope this was